Hi, my name is Jacob Mirth, and this is my video report for Intro Physics 1, Lab 2, the motion of a falling object. First, we're going to go through an introduction of the lab. Then we'll look at some observed data from the tracker software. Next, we'll look at the predicted data from the computational model. Then we'll compare the two data sets and make some observations. Then, finally, we'll answer some key questions about the experiment. Let's look at some objectives for this lab. So first off, we're going to apply Newton's second law to a real-world scenario of a falling object to determine the effects of gravity and drag on its motion. Then we'll build a predictive model to predict the motion of the falling object. And just as a preview of the results of this lab, we're going to be able to understand how drag causes objects to have a terminal velocity. Here's some key ideas that I'm going to use for this lab. Mainly, we're going to use Newton's second law, F equals ma, to predict the motion of the falling object. You can see this rewritten as the velocity update formula in the bottom left. For this formula, we need the net force on the object. To get this, we're going to make the assumption that the only two forces acting on the object are gravity pointing straight down and the force of drag pointing straight up. You can see the formula that I'll use for these two forces on the right side. This is a short video clip that I used in the tracker software. You can see the paper cone falling straight down. You can see in this graph that at first it starts with a velocity of 0 and then increases velocity until it reaches a constant velocity after about t equals 0.3 seconds. Let's look at the predicted motion of the object when we assume that there is no drag. You can see this is a much steeper curve. This means that there is a constant acceleration, the force of gravity, acting on the object. This is the code I used to make that prediction. At the top we have the mass of my object, which was a paper cone. It weighed 5 grams. The initial position and velocity of the object are both 0. Delta t is 0.033 seconds. This matches the frame rate of the video. G is 9.8. B for this is going to be 0 because we're assuming for this specific model that there is no air resistance, which we'll look at later and see why that's false. And then as we move further down into the while loop, you can see that we apply Newton's second law here to find the net force, which then we can use further to find the velocity, and then ultimately the position of the ball across different time intervals. Here's the predictive model for the ball, or the cone, when we do include drag. As you can see, this matches the actual data set much closer, which we'll look at in a little bit. But you can notice that the velocity makes a sharp decrease at the beginning, and then kind of flattens out here at a constant velocity towards the end. This is called the terminal velocity. Here's the code I use for this model. The only difference here is that b is a positive value. B represents the coefficient of drag for the object. And since we use b here, we have to incorporate that into our formula for net force, which you can see here. Here's a comparison of the three data sets. The blue line is the observed data set, so the real world. The orange line is the predicted data set that we just went over, that includes drag. And the gray data set is the prediction that does not include drag. As you can see, the real world data set with our predictive model that includes drag are very close together. So some observations from this experiment. The observed data accurately matches the predicted effects of gravity and drag on the paper cone. For a short time at the beginning, the force of gravity is larger than the force of drag, so the velocity of the paper cone increases. Finally, the terminal velocity of the paper cone was met very quickly. This is due to the high coefficient of drag on the paper cone, causing a high force of drag, combined with the low weight of the paper cone, causing a low force of gravity. Let's answer some key questions about this experiment. First, what does this mean? F net equals 0 at terminal velocity, because when the force of drag cancels with the force of gravity, our net force is 0, which means that the velocity will remain constant. F net is only greater than 0 when the force of gravity exceeds the force of drag, which only lasts for a short duration of time at the beginning of the experiment. And finally, the paper cone reached its terminal velocity. What if the paper cone was thrown down at t equals 0? As you can see from this graph, I actually plugged this scenario into the computational model by changing the initial velocity to -3 meters per second. As you can see, it actually reaches its terminal velocity much quicker. This is because, in the formula for drag is calculated by the drag coefficient times the velocity squared. So the higher your initial velocity, the higher the force of drag will be.